All right, our next guest, you know her as Lexi Lambda, her stage name. Alexis King is with us, a prolific contributor to Racket, coder, going to tell us about Hackett, a wonderful new. And I was so interested to find out that as a young person, you're so interested in 70s prog rock. Is that? So we've got that going for it, too. So please, take it away. A warm welcome for Alexis King.
All right, so I am going to be talking today about a programming language that I've been working on. It's called Hackett, and just as Proust does not have anything to do with French literature, Hackett does not have anything to do with progressive rock. In fact, the name is a convenient coincidence. Happens to be named the same as Steve Hackett, the guitarist of Genesis, but what it's really named after is two programming languages, which are, of course, Haskell and Racket. So in that sense, what is Haskell? I would imagine most people in this room have at least heard of Haskell, but maybe not everybody, and probably a lot of people don't really know that much about what it is or how it works. So it's a pure functional programming language, and it has static types. It has nice type inference. You don't have to specify very many type annotations. They can mostly be inferred. It has algebraic data types and pattern matching. So this is some Hackett code. This is some actual code in my programming language, but it demonstrates some of the features of Haskell. So you can define algebraic data types. You can pattern match on them. That's kind of how you build up data and how you consume it. It has type classes, and this is sort of the really interesting thing about the Haskell type system. It's what makes it sort of unique, is you can basically change the behavior of your program based on types. You can do kind of type-based dispatch, and I'll get more into that in a little bit. And it also has, this isn't technically standard Haskell, but Hackett implements it because it's really useful. It's this sort of notion of higher rank polymorphism, where you can have for alls to the left of your function arrows, which allows you to pass polymorphic functions to other functions. So these are kind of the basic Haskell features that are implemented in Hackett. But of course, it's a Racket language, right? So it's a hashling. You can write hashling Hackett at the top of your program, and you can use all these nice things. And of course, the biggest feature, the most useful, is that it has hygienic macros. So this is do notation from Haskell implemented in Hackett. This is the actual implementation. It's about 9 lines of code. And you can see that it's just using syntax parse. So you can use all of the nice existing hygienic macro tooling that you want, but in a Haskell-like language. You also get all of the sort of editor tooling that you like to have in Racket, Dr. Racket, Racket mode, the package system, cover. They all just kind of work out of the box. And you have access to the Racket ecosystem. Now, there's currently not a contract-protected FFI like there is with typed Racket, but there's not any fundamental reason why that can't exist. So eventually, there will be kind of the ability to consume Racket libraries from Hackett and Hackett libraries from Racket. So to be clear, Hackett is a Haskell implemented in Racket. So typed Racket is very much, you write your Racket program, you can add types to it. That's not what Hackett is. There's no dynamically typed Hackett. It's just Haskell. But the nice thing is you have the syntax model of Racket, so you can write those macros. So when I was sort of putting together this talk, I was thinking, well, what can I talk about? I can talk about algebraic data types and type classes and types and how nice they are. But then I would just be giving a talk about Haskell, right? And really, there's much better talks about Haskell, much better ways to learn about Haskell than for me to talk about it in this context. So I want to actually talk about something a little bit different. Why do I care about types in the first place? Why am I writing a typed language in the Racket ecosystem? And usually the answer to this is you want to catch bugs, right? We want to basically say, oh, I have a thing that's an integer and I'm using it as a string. I want to know at compile time that that's wrong. And so if you look at, say, typed Racket, that's what the type system does. You can write a function. You can say this is a function that takes an integer and produces an integer, and you can call it with an integer, and everything's great. But here's the thing. When you have programming languages like this, you can basically just throw away the types, and now you have a hashling Racket program, right? It still works. You can still run the program. It works exactly the same way. And so the notion is that most programming languages, whether they're typed Racket or Flow or TypeScript or even Java, C#, a lot of programming languages that are typed, they don't really use the type information. They're just a verification pass. And to me, this is kind of disappointing because you do have to contort your program a little bit to make it satisfy the type checker. And I want types to do a little bit more for me. So Haskell has the ability to make that possible. So with Haskell, if I have a function called pure, which is a type class, a function that's a method in a type class, what would this evaluate to? And the answer is you genuinely don't know. There's no way to know without knowing what the type of this expression is. Because if I say, I add a type annotation and I say, I want this to be a maybe value, an optional value, then I'll get back just 5. If I want it to be an either value, I'll get back right 5. And this is really interesting because it means that now I can use the types that I didn't even specify. I didn't write any types. Well, I did here, but most of the time they're inferred. And it will actually change the behavior based on information about your program. And that can be really useful. And this doesn't even have to be functions. So there's a value, m0. It's kind of this notion of an identity or an empty value of a monoid. And so if I say I want a string, then I get back the empty string. If I say that I want in a maybe, I get back nothing. If I say I want a list, I get back nil. And so this is really interesting, and it lets you abstract over things in different ways. So from my point of view, types are more interesting than just a way to verify that your program is correct. And in fact, in the context of metaprogramming, they're even more interesting because they can serve as a principled model of propagating compile time information. So that's really hand-wavy. What does that mean? Well, Racket has this notion of macros that communicate. And this is, to me, one of the most interesting features of Racket. It's why Racket is really cool. So I'm going to steal an example from, I think, a talk that Robbie gave. I don't even really remember. But basically, it's this notion of, let's say we have 2 macros in hashling Racket, one called define enum, one called enum case, where we define an enumeration, and then we pattern match on it, right? Pretty simple. So what we might want these macros to do is say, well, if I forget a case, right, if I leave one off, then I want, at compile time, the compiler to tell me that I forgot one. Or even more realistically, maybe I did include all 3 cases, but I add a new case later. My program changes. Feature request comes in. I need to support a new sort of animal. And so now I want the compiler to tell me all the places in my program that I have to change just to support the change. So in ordinary Racket, this is not hard. We can write a couple of macros that do this. And so I didn't include the full definition of enum case, but the basic idea is at some point it's going to call a function called syntax local value. It's going to look up that set that's defined by define enum, and it's going to see, are all those elements actually in the set, and are all the elements that are in the set actually provided by the user. And with these 2 things in place, if we leave off a case, then we get a nice compile time error message, and that's really nice. But, there's always a but. What don't I like about this program? What I don't like about this program is that I had to specify what I was pattern matching on. Now, this is a really contrived example, of course. It's a really minor burden to specify what you're pattern matching on. But the point is that I, as the programmer, obviously know what I'm pattern matching on. So that's just boilerplate. It's a very small amount of boilerplate, but in larger examples, it can be much bigger. And as a Racket programmer, I want to eliminate as much boilerplate as I possibly can. That's why I love macros so much, or one of the main reasons I like macros so much. I don't want to ever have to repeat myself. So Racket does have macros that communicate, but for the most part, that communication is fairly ad hoc. You either have to pass an identifier explicitly, or you have to have a macro that has a syntax property of something that some other macro reads, but as soon as you have a function call between your macros, then that information gets lost. And that's disappointing to me as a macro author. So type inference, as it turns out, we can not just view it as a way to verify that a program is well typed, but we can also use it since we have macros, to propagate information through a program automatically, even through function calls, even through passing values around in complex ways. So for example, we have pattern matching in Hackett, and when you pattern match on something, if it's non-exhaustive, I didn't have to specify that I was pattern matching on nothing here. The type inference figured that out, and it will give me a pattern matching exhaustiveness warning. Now, this might seem obvious. It might seem simple, because every Haskell-like language has exhaustiveness checking. But it's important to understand that exhaustiveness checking is not really part of type checking. It's kind of an additional pass. And it uses that compile time information. But because it's available to us, pattern matching is just a macro, right? It's not part of the type checker. But it still is able to consume that information and make decisions based on that. So this is a really contrived, simple example. But imagine a bigger one. So this is now going to be a little bit more aspirational. This is not something that really exists. But it's one of the things that motivated me to think about these things in the first place. SQL is error prone. If you want to write a SQL query, you have to construct a big string. You send it off to the SQL database. And then at runtime, maybe you get some cryptic error message back. So how do we solve that problem? Well, we can teach the language about our schema, right? And you can do this in Racket. This is hashling Racket. We can define a macro called define persistent struct or something like that. And now we can query simple data. We can define a structure that has sort of it's an identifier that has which table the identifier is from and its value, its primary key. Then we can pass it off to a function called get, and we'll get the value back. But for these CRUD operations, this is really simple, this is really easy, this is sufficient. But sometimes we want things that are more complex than this. So, of course, this being Racket, we can define a schema-aware query language, right? That's awesome. And so now when we query this user table, it will bind user.email and user.password, and then we'll be able to use those bindings to construct a query. And we're able to do that because, again, there's some compile time information bound by define persistent struct, and then the find macro consumes it. So this seems great, but we have another problem, which is that, hey, that thing snuck in again, just like for enum case. And again, this is a small example, but in the larger sense, this sort of thing crops up everywhere, where we're doing dispatch on information that we know, but the macro system doesn't know about it, even though it's in all of our heads as programmers. So imagine you have types, like in Hackett. This is an imaginary Hackett program, where we're basically writing a function called handle login. You give it an email and a password, and it uses some monadic do notation. It's basically going to call find. And we didn't specify anywhere in find which table we're querying from. So how does it know? Well, we have this function down here called setSession/redirect, which you can imagine it's returning a HTTP response, essentially. We give it a user, and it redirects back, adding that session onto the response. So because we have type inference, we then know that this user has to be a user. And we know that maybe user has to be a maybe user. That's pretty obvious. But then we know that this expression has an expected type, which is that it needs to produce a value of IO maybe user. And ideally, the find macro should be able to read that information and then use that because it knows about users. Users are something that, again, are defined by something like that define persistent struct macro. So then it should be able to bind the relevant things. But this is hard. And this is hard because this backwards inference process is tricky. What if you have a macro that needs some information to expand that depends on some other macro? That gets really hard. So we need a more principled way of doing this. And it turns out that Haskell's type classes are kind of a special case of this already. So type classes already require information. They already require us to expand the types before we can specialize them. So this plus plus operation is this notion of a generic append. And so when we expand this program, we'll say, all right, well, hello and world are strings. Therefore, we need plus plus on strings, right? But we need to expand the program in order to know what the types are. So this is kind of problematic because we need to change the expression after we've already inferred the types, but inferring the types requires expanding the expressions. Again, we kind of have this circular dependency. So one thing we can do, and the way Hackett kind of works right now, is we can perform two passes of macro expansion. So the idea is that on the first pass of macro expansion, we just expand into #app from Racket, and we leave kind of a placeholder in there. This red stuff is unexpanded. And then eventually, we'll expand the whole program, and we'll learn that that T in that expression is actually a string. So now at this point, we can go back in, and we can expand all those placeholders with all the information that we know about our program, and we can substitute in the fully expanded value. So the basic idea here is that we could have a programmable constraint solver. And that's really interesting to me because if you're familiar with Haskell's type system, it adds all these wonderful features that are technically not coupled to the particular constraints. They're not coupled to type classes. So things like implicit parameters, units of measure, and even kind of entirely type equalities, things that you might not even traditionally think of as constraints could be added by users, not the author of this programming language. So the reason that's exciting to me is because what that allows you to do is kind of make the information provided by macros perform a full program transformation, like type classes are, in a composable user-defined way. And this is not, again, something that's currently in place, but I think it would be really neat, and it would allow Hackett to do things that neither Racket or Haskell can do in isolation. So to recap, Hackett is a Haskell that runs on Racket. And today, it cooperates with Racket's hygienic macro expander. It supports Haskell idioms. It integrates with Racket's language tooling. All of these things are in place today. You can use it. You can write #Hackett at the top of your program, Racco package install Hackett. You'll be able to write real programs. Soon, I hope that you'll be able to write actually useful programs, right? Because there's not a very large standard library right now, but there's not a whole lot in the way of making that possible. It also probably needs to be a little bit faster. Error messages need to be a little better. Also, I'm hoping that very soon it can have more Haskell features. So things like multi-parameter type classes, functional dependencies, default type class methods. There's already a lot there, though. So it's already something that you can theoretically write, but it would be nice to have a little bit more. Stuff like type families are probably out of scope for the immediate future. But eventually, I'd like to have a typed Racket-style, contract-protected Racket Hackett FFI and a programmable constraint solver. So with all those things in place, I think Hackett would be interesting in the sense that you would be able to do, again, more things than Haskell, but more things than Racket, just because by combining the two, you get something that's a little bigger than the sum of its parts. And that's it. Any questions?
Terrific. Thank you, Alexis. Questions for Alexis? Prabhakar.
I don't know much about template Haskell, so maybe I can't understand the answer, but can you compare and contrast template Haskell and Hackett today?
Sure. So that's a question I've been asked a few times, so, but it's fine because my answer has evolved over the months.
Repeat the question.
Yes, thank you. Of course. The question is, can I compare Hackett and template Haskell? So for those not familiar, template Haskell is Haskell's, I hesitate to call it a macro system. It's really a splice system. And that's useful. It's very useful. I would say a lot of idioms that are in place in Haskell today would be impossible without template Haskell, lenses being one of them. But the basic idea is that macros are a code-to-code transformation, right? Template Haskell is not a code-to-code transformation. It's that you can call a function using Haskell syntax, and the result will produce a Haskell AST. It'll produce code that gets spliced into the program. So that in and of itself, like you can't define new syntactic forms with that because you're not allowed to define new syntax. The bigger problem is that template Haskell is fairly restrictive. If you define a group of definitions with template Haskell, then it breaks up the whole program and type checks like the first half of the program, then the second half of the program, and you can't use definitions under. So mutually recursive things are basically impossible. And for expressions, they just don't have access to the same amount of type information. And the reason for that is because Haskell's type system was not designed with this in mind, so Hackett kind of interleaves type checking and macro expansion to make that possible, whereas template Haskell doesn't. So it's probably.
One more question in the back. Matthias. Oh, it's going to be a good one. It's Matthias.
Oh, no.
I want to thank Alexis.
Yeah. The question is, because Haskell is lazy, when you do interop with Racket, which is strict, how do you know when to force the laziness? And astute observers will notice that I never said the word lazy in this entire talk. And that's because I have not actually committed to a evaluation model.
Don't.
It is currently lazy, but that's kind of a side effect of it turned out to be easier to make it lazy based on some problem I was running into. But I would actually probably, I'm not sure about that.
Could you explain the problem?
Yeah, it's basically just that type class elaboration pass where you turn type class constraints into dictionaries. It turned out that I was having forward references that were getting evaluated too early. Where Racket was complaining, hey, this is being used before it's defined. And it was really easy to just introduce a couple of delays and a couple of forces, and the problem went away.
How do your dictionaries interact with the module system? Because they're centralized. The dictionary is central.
There's a phase one dictionary of type class instances, and I can explain in more detail how it works. But the global instances that you think of people defining, just like how you would normally do it, there's like a begin for syntax in the modules that define them, and they store them into the mutable dictionary. That's it. There isn't currently actually detection of orphans or even, I think, overlapping instances, but I've actually done something very similar to that in the past in untyped Racket, so I don't think it should be hard to add.
All right, we can take the rest of the questions because we have a break coming up, but one more hand for Alexis King. What an amazing project. Thank you very much.